Thanks, the organizer, for the opportunity of this talk. And for those of you who don't know me, I'm Nicola Tamanini from L2IT in Toulouse. For those of you who don't know me, it's a great pleasure to meet you all after so many years of online meetings. It's nice that we're all together here again. Okay, what I'm going to discuss, what I'm going to discuss today is try to show you how we can measure the expansion of the universe with LISA. So I will go through the methodologies first, try to explain the concept. I will not have time to go into the details. Then I will briefly show you the current results with LIGO and Virgo, and then I explain you all about LISA. All right, so let's start with the concept, which is standard sirens is the main, let's say, methodology here. The idea is how to go basically from the waveform that we detect, so the signal that we actually detect with gravitational waves, to the expansion of the universe. And the main concept is quite simple to understand. So this is the, let's say, waveform we detect at the detector. This is just an example at the lowest order what we can see in mathematical terms. And one of the most important things here is that we can detect the distance to the source. So the luminosity distance to the source is basically one of the parameters that enters the waveform, and in particular the amplitude of the waveform, which means that whenever we do parameter estimation over our gravitational wave signal, we get an estimation of the luminosity distance for free. Now, this is a distance at cosmological scales, which is completely independent by the cosmic distance ladders. If you are a cosmologist, you know that in order to measure distances at, let's say, redshift 1 or even below very high distances, let's say, you need always to calibrate supernovae or whatever methods you're using with more local sources like Cepheids and so on. This might introduce some systematics that we are unaware of, and standard sirens are a way to basically get distances, cosmological distances, without any systematics. But we need a redshift to do cosmology because we want to test the so-called distance-redshift relation. This is a relation in cosmology that basically connects the luminosity distance to the redshift of each point or source in the universe. So if we have a measurement of the luminosity distance and a measurement of the redshift, we can do basically a fit of this relation here, which is the luminosity distance relation, and basically get constraints on cosmological parameters for free. This is exactly the same, or very similar to what supernovae do. The only difference is that we get the luminosity distance for free, and we really need to struggle to get the redshift. So how do we actually get the redshift of the source? So you might have noticed that the expression here for the signals, gravitational wave signals at the source, is independent of the redshift, so we need other methods to actually get the redshift. So there are three main ideas that are used nowadays to get redshift information. The first one is the most intuitive: get a counterpart, thanks, and we get the redshift for free. The idea is that you detect a transient, you associate with confidence to the gravitational wave signal. From that, you identify the host galaxy. From the host galaxy, you get the redshift. That's perfect. This is exactly what happens for supernovae, for example, where you have various emission after the merger in different timescales, and you might be able to detect the afterglows or the kilonova or the gamma ray burst and so on. However, even if you don't have a counterpart, there are other methods, what is called dark siren, in comparison with the bright siren, where you have a counterpart. And the idea here is similar, but is a bit more complicated, let's say. So you take the sky localization region of your gravitational wave source, you take a galaxy catalog, and you basically look at all the galaxies in the sky localization region. Conceptually, it's very simple. So if you are lucky, you have a few galaxies in your region. If you are unlucky, you have a lot of galaxies. What you do then, for each of these galaxies, you associate a redshift. And for each of these redshifts, you will basically have a corresponding measurement of your cosmological parameters. For example, if you are in the local universe, your redshift measurement directly translates into a measurement of H0. So you will have basically different measurement of H0 for each gravitational wave signal. In the case you have one signal, of course, you cannot do anything because you will have a lot of galaxies, or you will have a lot of different measurements. You can even be biased, like in this example. There is a big cluster nearby, so your measurement is probably be biased. If you keep stacking events, though, at some point, everything level out. And at some point, if you have enough events, you can get out, basically, statistically, the true value of your cosmological parameters, simply because the true value, the true galaxy, is always within your scalar gravitation volume, like all the other galaxies that gives you, let's say, say, untrue parameters. They will average out and basically cancel in the final posterior. There is another third method that has been developed in the last, let's say, 5 years, mostly. And this is what we call usually spectral sirens, or dark spectral sirens, because we don't use an electromagnetic counterpart also in this case. The idea is quite complicated. I'll try to make it simple. So suppose that all your gravitational wave sources come with a mass that is given at the detector. So basically, sorry, at the source. So basically what does it mean is that the distribution of masses of your population at the source is a delta function on some mass, source mass here. This means that whenever you detect a source in your detector, then you get the redshift for free, because you know the mass as the source, and then you know the two masses, the one observed and the one at the source, are related by the redshift. Okay? That would be ideal. We could do cosmology really easily like this. However, we don't get a delta function distribution at the source. We get something more complicated. So you basically have a distribution of the mass at the source, and you have your distribution of the mass at the detector, and you can connect them statistically through the redshift. This is basically the same idea that if you had basically a delta function. The only thing is that it's more complicated because you have a distribution which is, let's say, more complicated. So what you have to do is basically model your distribution at the source. So you have some phenomenological model. These are the ones, for example, used by the LVK in the O3 data release. And then what you do, you fit for this model together with cosmology, and you get cosmological parameters out of this. This method is really dependent on the modeling of the population at the source. So we might introduce systematics, and it's still a lot in development, especially if you are considering, for example, that the mass distribution evolves in redshift. That complicates a lot of things. This will be fundamental for LISA, and for this I encourage you to look at the poster by Vasco Gennari that is looking at this problem. So let's briefly show you the current results from LVK. To flash, and don't have time to go into the details. I really want to go to LISA. So this is the situation more or less right now. So we had 3 completed observational runs. The 4th one is ongoing. We are in O4B. O4A is just finished. And this is the cumulative detection over the years or over time, let's say, together with the current candidates from O4A. The most important point that you have to take from this picture is that starting from O3, basically we can do population analysis because we detect one source every week, let's say, in O3, and now in O4 almost every 3 days. With this, within these sources, let's say, of course, the most important, and I think everyone here knows, is GW170817. This was the first ever standard siren that has been used, and it's a bright siren in the sense that we detected the electromagnetic counterpart. So after the gravitational wave signal, we managed to see the gamma ray burst, and to see afterglows and kilonova in different electromagnetic band. With these measurements, we were basically able to give constraints on the Hubble constant, which is the following one. So basically, the idea here is, again, you just have a simple measurement of the redshift, a simple measurement of distance. You fit the Hubble law because the event was in the local universe, and you get a measurement of the Hubble constant. This is compatible, largely compatible, I would say, with current measurement from Planck and supernovae. Of course, it's not comparable in uncertainty with them. I just flash you also the results we have with the dark sirens, because we started to use dark siren in LVK to test cosmology. You can use all the binary black holes with these methods. Nowadays, dark siren contribution is marginal, so it's let's say, 20% improvement over GW17 or 17, but this is going to improve in the next run. And for the future, here, the point with the current detector is to get down to a few percent in reliable constant to solve the tension. Here I want to highlight that we really don't know when we will be able to arrive here. So if you take supernovae and CMB, it took 10, 15 years to go down from order 10% to order 1% constraints. If you take the same time for gravitational waves, we might be in the race with LISA to get a nice constraints on H0 comparable with, if not with the electromagnetic constraints, unless with other gravitational waves observation. And I invite you to see a poster by Nicola on future interesting forecast with ground-based detector. So let's go to LISA in the last 6-7 minutes that remains to me. So LISA will see different sources at cosmological distances. So everything that basically we detect outside our galaxy, we can use it for cosmology. So there are stellar mass black holes, and I cross them out, and you will understand why in a minute. There are intermediate mass black holes, and I put a question mark on that because we don't know if they are there and how many. And of course, there are extreme mass stretching spirals and massive black hole binaries. The last one, we are some possibilities to detect the counterpart, so they can be used actually as bright siren. So first of all, stellar origin black holes. We had few results a few years ago that were saying that will be really good for cosmology. Unfortunately, since the design of LISA evolved, now the high frequency band of the signal of the sensitivity curve is slightly worse than a few years ago, which means that nowadays we are not expecting many sources, stellar origin black hole source, let's say, which means that unfortunately we cannot do cosmology anymore. However, there are some more new ideas that people is trying still to develop, so you can have a look at Sukanta Bo's talk this afternoon. Intermediate mass black holes, if they are there, they will be the perfect sources for multiband, because let's say 100s, 200s, even 300s black holes, we might be able to detect them both with LISA and Earth-based detector. If they are there, and if they are numerous, let's say with order 5 sources, we get 1% constraint on H0 for free. Unfortunately, nobody knows yet how many there are. MRIs, these are perfect standard, let's say, dark siren sources, in the sense that if we detect a lot of them, and again, here the rates are really uncertain, then the well-localized one will be really useful for dark sirens. And there is a nice work by Danilagis that basically showed that you can get H0 between 1 and, let's say, 10%, depending on the population of MRIs. And you can also start measuring the equation of state of dark energy. So you can see actually different realization and different number of sources. You can get down to a few percent of on H0. MRIs might also be lensed. So if you get just one lensed MRI, it's going to be a really interesting source. So the signal is going to be really complicated because it's superposition of 2 images of MRIs. So really complicated to analyze, but suppose you can get it and analyze it. Then we might even get the host galaxy, because if this signal will be well localized. So you are looking for a galaxy which is lensed in a well localized region. So it might be that we have a good opportunity to get the counterpart. And if we get one, let's say a redshift more or less 1 or below, then you can get H0 to 1% with just one source. This will be really interesting. Finally, massive black hole binaries. These are the, let's say, main target source for LISA. They are expected to basically merge in a gas-rich environment, or at least in many models they merge in a gas-rich environment, which means that they can produce electromagnetic counterpart through different effects. What we analyzed in this paper led by Alberto Mangiagli is basically the number of counterparts you can get depending on different assumptions and different detection, different telescopes that you will use to look for the counterpart. The main idea is that you can get counterparts up to redshift 5 or 6, but not in great numbers. So here are the numbers that you can get in a 4 years mission. So they go from, let's say, 20 counterparts in the most optimistic case to, let's say, 2 or 3 counterparts in the most pessimistic. However, if you have even few of these counterparts, you can get H0 to really few percent. So here is the cumulative distribution on the fractional error on H0. So in the median case, we get, let's say, from 2 to 6, 7% on the H0. Omega m, we can measure it at the 10%, 20% level. But most importantly, what we get with the massive black holes is that at high redshift, we get a really good measurement of the luminosity distance relation. So here you can see a reconstruction of the dl of z. And you can go to basically few percent up to redshift almost 5 or 6. And I really strongly encourage you to have a look at Alberto Mangiali's talk this afternoon, which will go into the details with all of this. And of course, this is also useful to test lambda CDM at high redshift and to make, let's say, probes the nature of dark energy and modify gravity. So you can test, for example, an interaction in dark sector. You can check against the the quasar-Hubble diagram that is being constructed nowadays at high redshift. And you can also detect, modify gravitational wave propagation and check this really effectively. All of this can be put together. The main two sources that I just presented are MRIs and massive black holes. If you put them together, these will be really strong constraints. For example, on lambda CDM, you will be able to break some of the degeneracy in the parameter space. And we expect to get, let's say, 1% or below 1% constraint of H0. I really invite you to, again, to see Danny Laghi's talks this afternoon. He has preliminary results on the combination of these sources, so I don't want to spoil anything. If you are interested, just go there and have a look at the code. So this is a big table that summarizes all the constraints we can get with LISA, with different sources and so on. I didn't talk about lensed massive black holes because they probably are not so numerous, but the idea here is that if you combine all of this together, we of course expect to get better than 1% constraint on H0 and to get high Z, so high redshift and dark energies analysis for free. And this is all what I wanted to say. I leave you with my conclusion because I see the time that gets 0 and is blinking. The most important thing I want to highlight is that we might be in the race to solve the Hubble tension, or at least to give nice constraints on the Hubble constant on time frame comparables with the Hertz-based detector. Thank you.
Thanks very much to Nicola. I think we got time for some questions. Yep, go ahead.
It's all right. It's more time for questions.
Hi. Real quick, I was surprised to hear you talk about IMBHs as multiband with the ground. Could you say what masses you are considering and what detectors? Like, I'm assuming 3G of some kind.
Yeah. So there is this nice, I can go back to the slides. This nice paper led by Nicola Muttoni that looked at masses between 100 and 500 solar masses, let's say. So these are masses that you can detect with 3G, especially if you have ET with the cryogenic, let's say, technology. So you can go below, down to, let's say, 1 Hertz or few Hertz. And you might see the merger of these sources with the Hertz-based detector. And you will see the spiral, let's say, quite loudly in LISA. So this is the idea. But the problem, of course, is we don't know how many they are.
Okay, any more questions? Over in the corner here.
Yeah, so besides the race against ground-based, there's also the race against other probes like tip of the red giant branch. So is there something uniquely that space-based probes can do, like a specific redshift range?
So this is what I wanted to highlight at the end, but maybe I went too fast. So the fact that LISA will see sources at really high redshift, so if we are lucky, we can get massive black hole binaries with a counterpart up to redshift 5 or 6. It's something that is impossible to do with supernovae, because you will never detect supernovae above redshift 2, let's say, or at least not in the foreseeable future. There are quasars that are being used as standard ruler nowadays to check that kind of redshift range, but they are very uncertain. They rely on phenomenological relations that are still being tested, let's say. So this kind of, let's say, constraints in this redshift range will be really useful to check if the expansion of the universe is actually lambda CDM in that regime. It's a regime that is expected to be dominated by matter domination, basically, but we're going to check if this is the case. And if there is any deviation at that redshift, either given by modified gravity or some dark energy model that early dark energy models, we will be able to test it with LISA. So this is actually what I was trying to highlight here, that more than the H0 race, which I still believe it might be let's say, LISA might still be in the race, because we will see how it goes in the next 10 to 15 years. Then we can do really precise high-Z cosmography, let's say, because we can really test this region between, let's say, redshift 2, 4, and 3, well, 3 and 4, at the few percent level, let's say. So this is something that LISA will be unique in doing. It will be it will compete with the 3G detectors, because 3G detectors will detect binary black holes up to redshift 10 or 15. However, first of all, we still have to see if 3G detector will be there by the time LISA fly. And second, 3G detectors see a really different population of sources, so it will be a comparable check with them and, let's say, complementary constraints on the source population and on the cosmography at high redshift.
We maybe have time for one last question. Yep, here in the middle.
Thanks, Nicola. Maybe two quick ones. Do you call the Emery's dark sirens? What about TDEs? Are they not connected maybe to TDEs? That's one question. The other thing, very quickly, do you, for the massive black holes, and maybe even for the TDEs, do you really need Rubin, or do you think that's something you can do with, like, what's the predicted magnitudes, of course, with uncertainties? Do you really need Rubin, or do you think that's something you can do with already existing smaller scale?
Let me answer to your first question. I didn't get exactly the second question, so maybe you can say that again. So the first question is, yes, TDEs are sources that have been analyzed in the last few years, mainly by Martina Toscani and collaborators. They will be really interesting if we can detect them. Unfortunately, the rates so far in LISA are not so, let's say, optimistic. So we might see maybe one in the whole LISA mission, let's say. If we detect them with LISA in great numbers, and we also might detect the counterpart because they emit a lot of electromagnetic radiation, they will be the perfect standard sirens. But we need to demonstrate that we can get out the distance from these signals. And we need waveform for that. So it's something promising, but it's really far in the future to understand if we can use them for cosmology. They will be really interesting for DCR detectors, because you can see them in great numbers. But unfortunately for LISA, we still don't believe we can see them a lot. And what was the second question?
What's the predicted magnitudes for the counterparts for the massive black hole mergers? Do you need Rubin for that?
You need Rubin for that.
Okay.
It's like above 26, 27. It's really high.
Okay, let's thank Nicola again.